Okay. Hey everybody. Um Now it really is everybody. So Arseni I guess is still asleep. No worries. Today we'll be talking about chapters 1.3 and maybe a little bit of 1.4 in Hartshorne. So this is probably by far the hardest chapter that we're going to cover and also the most important one. So except for maybe when we do like a little bit of homological algebra, it'll be more difficult. We'll see. So yeah, we talked about quasi-affine regular functions. So basically, if you have open sets, I don't think it's necessarily obvious why we have to define regular functions on quasi-affine varieties. Um, and basically, the reason why is because we can define a topology on quasi-affine varieties, whereas just on affine varieties, they're closed sets. So quasi-affine varieties are open sets. And so we can define this topology where we get an open neighborhood. Um, and then, yeah, similarly, quasi-projective varieties have regular functions. And then the key difference is that polynomials have to be homogeneous and of the same degree. So the g and the f have to be homogeneous and of the same degree. Um, and so our gluing theorem is that if f and g are regular on a variety x, and that if they agree on any non-empty open neighborhood of X, then they agree everywhere. Um, and this is similar to what's called the pacing lemma in topology. Um, so that's pretty cool. Um, then we started talking about the category of varieties, and this is where shit gets complicated. Um, so basically, varieties of any kind are objects. Morphisms in the category of varieties are continuous maps that are regular, or sorry, continuous maps that for every regular f from an open subset in the codomain um, of the morphism, the function composition f circ phi from the inverse image of the open set into K is also regular. And what we talked about with isomorphism is really this is an isomorphism if it maps to the exact same thing. So I'll even put, I guess this even kind of goes in a weird way in terms of showing that something is a morphism. You get this kind of inverse relationship. And so basically, if it factors uniquely through F, then it's an isomorphism, but otherwise it's not. And so our two examples for morphisms which were bijective and bicontinuous that weren't isomorphisms um, were basically the twisted cubic in 2 dimensions, although that isn't what we said it was. But the twisted cubic we showed was not an isomorphism because of dimensionality. And then in the same dimension, we showed that the Frobenius morphism couldn't be an isomorphism, uh, basically because we had different dimensions of codomains, or of images. Now, the important thing to note here is I'm saying of images, not of spaces. The spaces themselves have the same dimension, and it is an isomorphism, or sorry, not an isomorphism. It is a bijective bicontinuous map. Um, the thing that forces this together is the pigeonhole principle. And so it comes from the dimension of the image of the inverse image of the open subset. All right, lecture 6. All right, AG seminar lecture 6. 1.3 continued. Okay. So today we're going to talk about rings of functions which are associated with varieties. And so this is where it gets just kind of to be a lot to keep track of mentally. We're going to have like 7 definitions here. And it's just kind of going to keep building. And so, yeah, feel free to pause, work through some examples, whatnot. So, let Y be a variety. No, we don't specify affine, quasi-affine, projective, or quasi-projective. So here we're just talking about in the category of varieties, this definition is going to work. No, that's not a nice enough O. There we go. That's a nice O. O of Y, it's very important that you draw it that way, is the ring of all regular functions on Y. So again, by the gluing lemma, we said, okay, 2 functions only have to agree on one open neighborhood for it to agree on all of Y. So the ring of regular functions work. And then if P is a point in Y, the local ring of P on Y OP is the ring of germs of regular functions on Y near P. And now, of course, you're asking, well, what is a germ of a regular function? Well, the germ of a regular function is an equivalence class of functions which agree near P. So the germ of regular functions near P is an equivalence class of functions which agree near P. And then, in other words, an element of the local ring at P is a pair U comma F where U is open in Y and or contains P. And F is regular on U. More importantly, U comma F is similar, we'll say, to V comma G if and only if F equals G on U intersect V. So this is our equivalence relation. Um, um, and then this is just kind of a fact. So, the maximal ideal of OP is the set of terms of regular functions which vanish at P. And so this is kind of where Hartshorne doesn't talk about what the hell a localization is. The localization by an element or by an ideal or by whatever is to do whatever makes sense in terms of saying to divide out by that thing. So this is kind of a pseudo definition, but the localization of something at P is to take x sub P is equal to all the x in x over P such that x in x. So in the sense of ideals, we don't literally divide because we can't divide those things, but we mod out by it, right? So divide where it literally makes sense to, otherwise mod out, quotient out. Okay. Yeah. There there really isn't like a great set of examples here. So the thing that just blows about this section is it's like just literally stock definitions. Um, yeah. Okay. So more definitions. Um, so again, if y is a variety, the function field of a variety y is k of y. And so an element of k of y is an equivalence class of pairs. U comma F, where U is a non-empty open subset of Y. F is a regular function on U. And where U comma F and V comma G, if and only if F is equal to G on U intersect V. And so you might be thinking, what the hell makes this different than the local ring at P? This is exactly how we set up the local ring at P. Well, this isn't the localization at P. So the local ring at P is the ring of germs of regular functions near P, which has this equivalence relation. So we're using the same equivalence relation, but the things that we are comparing is different. Here we don't have to contain P, we just have to be regular on U. And moreover, like, just for the ring of all regular functions, it definitely is not like a thing of equivalence classes. So basically, and I'll put this into a kind of a table form. OY, OP, K of Y, and I'll also go ahead and include A of Y, because it's in here. Are there any others that we're going to need? I don't think so. Oh, S of Y. Yep. So, if you ever get lost watching this recording, this is probably the spot to come back to. So this is A quotient I of Y, but more importantly, what is that called? Affine coordinate ring. Affine coordinate ring. A quotient I of Y. This is the projective coordinate ring. This is S quotient I of Y. This is the ring of regular functions on Y. This is the local ring at P on Y. This is the function field of Y. So yeah, this is I'm gonna name this. This is a pretty helpful chart. I'm gonna call this Figure 1. We will add to this later. We'll talk about the spectrum of a ring, but that's in a while. I think that's actually not until we get to sheaves. Yeah, I'm pretty sure that's not until we get to sheaves. So, okay. Sorry, it's 7 a.m. for me, so. Mm. Um, and so I guess the nice property, the thing about K of Y is that it really is a field. So K of Y is a field of functions. Um, and this comes out of the fact that since Y is irreducible, any two non-empty open sets have a non-empty intersection. So we can define addition and multiplication in K of Y. And then we restrict it to the part where it never vanishes. And that gives us multiplicative inverses for 1 over f. So the inverses are defined by 1 over f. So ky as a field. So 1, y irreducible implies that non-empty set have a non-empty intersection. Implies a plus b, a times b are well defined. So this gives it ring structure. Then if UF is in K of Y, we can restrict it to U minus U intersect the zero set of F. So just removing the spots where it vanishes. So F never vanishes. And what this means is that 1 over F is also, and really it's that U minus U cap ZF 1 over F is in K of Y. And really that's like kind of a very interesting construction on its own. Like that's, I think, a pretty neat thing. So yeah. And this is really all we need to do to make it a field. Like we have well-defined inverses. That's the thing you're missing from a ring in this case because we're working with commutative rings. Kind of implicitly, like to work in a variety in a meaningful way for intro algebraic geometry, it's going to be commutative. Like algebraic geometry has this subset, it's a very large subset called commutative algebra. Commutative algebra is all the stuff that we were doing with like Grosvenor bases. And more, of course, but largely a lot like Grosvenor basis is like a big thing. In such a manner, here we don't have to worry about commutivity because general assumptions of commutative algebra. Um, Yeah. And then I guess the implication here is that u comma f inverse is equal to u minus u intersect 0 set of f 1 over f. Right? So this is multiplicative inverse. And then by restricting, this is kind of like lemma. By reasonably restricting maps, we get a chain O of y into the localization at P into K of y. Which is injective. So thinking in terms of set cardinality, right? OY and OP are subrings of KY. So it's injective, meaning that we are like any 2 points that are the same in the codomain get mapped to the same thing in the domain. And it really isn't clear how all of this follows. I say greater than, it should really be like this. Basically, the ring of regular functions on y has to be the ring of all functions which are regular on all of y. So that's a smaller set than the ring of regular functions which are just at a point, or some open neighborhood of the point, which is smaller than the set of, or which is smaller than the field of all functions, which are regular on u. So it does kind of make sense. I don't know. If we replace y by an isomorphic variety, the corresponding rings are invariant. And so these are called the invariants of a variety y up to isomorphism. Y, P, and KY are invariant up to isomorphism. And what this means is that if we have a short exact sequence, don't really worry about what the zero means right now, but it's important that it's there for later. With that just looks like a G. Hold on. P K of X, and maybe this will be OP P prime. Alpha, beta, gamma. Are isomorphisms. Again, don't worry too much about the commutative diagram here. It does commute nicely. This is something that we're going to show later on when we deal with a little bit more homological algebra. Um, Again, kind of the rush for the three of us this week is that we get through Hartshorne because the first and it really this has not been well said yet. The first chapter of Hartshorne is an approach to classical algebraic geometry. And it's all of classical algebraic geometry condensed into like I don't know 60 pages. And so then he kind of like gets into sheaves and schemes, which are modern algebraic geometry. But at that point, we'll be following along in a different book. Um, so our next task is to relate OY, OP, KY to the affine coordinate ring of an affine variety and the homogeneous coordinate ring S of Y, the projected variety. And that's making me realize this shouldn't be projective coordinate ring. It should be a homogeneous coordinate ring. Okay. And so our motivation for this next section is that we're going to find that for an affine variety Y, um, that our affine coordinate ring is actually the same ring as our ring of regular functions. So it is invariant up to isomorphism. However, this is not true for S of Y. Arsony is up. Cool. He should be in here in a second. That will hopefully put life into my bones. I have a very hard time just like talking to a screen. Like I need people to like talk back. um, yeah. So, and actually we've only, holy shit. This feels like so much. Like this is so much. Um, yeah. Yeah. Yep, and then we get up here. Okay, I think we can do that. We're right a little bit below halfway. So let's hit theorem 3.2. Theorem. So let Y contained in the affine n space be an affine variety with affine coordinate ring AY. Then we have 4 points. Hey, Arseni.
Hey, I'm so sorry, Tim. I set up my alarm wrong.
Dude, no worries. I'm sure I have done or will do the same thing at some point to you guys. So just
Thanks.
use this as the rain check to cover the bill for that for
I will
me.
rewatch the lecture.
Yeah. I'll just real quickly go over this so that you're not lost. We defined just a bunch of different things on varieties. And so we're talking about the category of varieties as a general thing, and then now we're specifying again. So we have if y is any variety, O of y is the ring of regular functions on y, which are functions which can be represented as rational functions at every point. If P is a point in Y, the local ring of P on Y, which is just O script or subscript P, is the ring of germs of regular functions on Y near P. Well, what are the germs of regular functions? Well, they're an equivalence class of functions which agree on P, or near P. And so basically an element of OP is a pair UF, where U is open in Y, contains P, and then F is regular on U. No clue why I read that twice. And so basically our equivalence relation is that if you have two pairs, UF and VG, they're similar or congruent if and only if F is equal to G on the intersection of their open subsets. And then the maximal ideal of a local ring is basically the set of germs of regular functions which vanish at P. And so this actually tells us a lot about the global structure of the ring based off of local rings. And the reason I emphasize that is because we will later talk about a type of ring which is going to tell us about hyperlocal structure, whereas this actually tells us about global structure. Then we said that the general localization of some anything x at P in X is to take XP is equal to either the quotient or the literal division X over P. And it is completely dependent on what structure you're working with. Like if you're working with polynomial rings in general, we usually can't divide polynomials, at least not meaningfully. And so usually it'll mean mod out by like the ideal generated by those polynomials. But in some cases, it literally does. Like if you're taking a number ring and you want to localize it 2, in the integers, well, then it's just all of the numbers divided by 2. So the function field of a variety is k of y, and an element of k of y is an equivalence class of pairs completely identical to the local ring at P, with the key difference of it doesn't contain P. And so this is just all of the functions under that equivalence relation, which are regular on Y. So they don't have to be containing P. And so this generalizes some things. And I set it up into a little figure here. So A of Y is the affine coordinate ring. S of Y is the homogeneous coordinate ring. O of Y is the ring of regular functions. O sub P is the local ring at P on Y. K of Y is the function field of Y. It may help to write down this figure specifically just so that you have like the names of things. Because I'm not going to lie, it gets really difficult to keep track of. Give me a thumbs up whenever you finish. All good? Or, yeah, okay. So, basically showing that KY is a field, well, since Y is irreducible, any two non-empty subsets have an intersection which is not empty. I didn't write that part down. A intersect B is not empty. And then this means that we can define sums and multiplication on them. And so the way that this works to get multiplicative inverses to help make it, at least a field, is to restrict any map, F on U open in Y to anywhere in that subset where it doesn't vanish. So it's just U minus all of the things in U where F would vanish. And so then we get that the multiplicative inverse of U comma F is this thing 1 over F where F never vanishes, so we don't divide by 0. And so it just kind of works the way we want it to. And then we said that by reasonably restricting functions, we get this chain which is injective. What this means is that K of y contains OP and O of y as subfields. Or sorry, as subrings, not subfields, subrings. And then the three of these things are invariant up to isomorphism, meaning that we can swap out the variety. And basically, if two varieties are isomorphic, like x isomorphic to y, and maybe I should write that in. If x is isomorphic to y, then their rings and fields are the same. And so the motivation for this next section is that for affine varieties y, A of y is actually, like the affine coordinate ring, is just the ring of regular functions. And so it's invariant up to isomorphism, but this isn't true for projective space. And so theorem 3.2 is kind of a large one. We have y is an affine variety with an affine coordinate ring A of y. And so then the ring of regular functions is isomorphic as a ring to y. And the reason why I say ring isomorphism is because we have the isomorphism of varieties versus the isomorphism of rings versus the isomorphism of categories. There's a lot of morphisms floating around, and all of them have different embedded structure. So it's really important that we kind of specify here. Part B is for all points in the variety, let MP contained in the affine coordinate ring be the ideal of functions vanishing at P. Again, this is this idea of localization that I talked about earlier. Then P getting sent to its localization ideal gives a one-to-one correspondence between the points of y AY. Sorry, I think I lost you for a second. Basically, P to MP gives a one-to-one correspondence between the points of y and the maximal ideals of AY. And then for every point P and Y, the ring of regular functions localized at P is isomorphic to A of Y localized at MP. So again, this is where we mean mod out by MP. And this is why I hate this notation so damn much, because nobody explains it in any of their books, because they're like, well, some algebraic geometry book covered it. No, it didn't. None of the 6 that I own did. So, anyway, something about keeping priests out of the temple, so to speak. And then the dimension of the local ring at P is equal to the dimension of the local ring at Y, either via Kroll dimension or the induced topology dimension. Finally, K of Y is isomorphic to the field of fractions of A of Y. And we don't actually have a way to really denote this except for A of Y Cartesian product A of Y, I guess would be the easiest way to do it. Yeah, that's probably the easiest way to do it. That's isomorphic to the field of fractions. And so k of y is a finitely generated extension field of k with the dimension of y equal to the transcendence degree k of y extend k. So you remember this notation from Galois theory, right?
Yeah.
Yeah. Okay, cool. So, I really don't want to prove this. So I'm gonna like just yap for a little bit. And if in yapping I decide that I need to prove it, then fuck, here we go. Yeah. So local ring being isomorphic to affine coordinate ring. Sorry, not local ring. The ring of regular functions being isomorphic to coordinate ring. Well, we talked about continuous functions. Notably, continuous functions are regular functions in affine space. And by pushing that definition through, you can convert one to the other pretty quickly. The main key difference is that all the functions that we're representing in the ring of regular functions on Y are parings with their open subsets that they are, with. That a function is regular on, then we get everything that we want. As far as set containment goes, whatever. Okay. So MP being this maximal ideal of AY vanishing at P, sending P to MP gives a one-to-one correspondence between the points of Y and the maximal ideals of A of Y. Basically, this we know that there's a one-to-one correspondence between points of Y, which are the minimal algebraic subsets of Y, and then maximal ideals of A containing Y. And then passing to the quotient of the ideal generated by the variety, these correspond to the maximal ideals. And then if we just have a function which sends stuff from our polynomial ring into the ring of regular functions, we can actually identify these immediately with regular functions on Y. And so the maximal ideal corresponding to a point is just this MP, which is the ideal generated by the variety. Now for C, every point in Y, the localization at P is isomorphic to A of P localized at the maximal ideal generated by P. Okay. Well, basically this hinges off of the fact that we can send things straight from the polynomial ring to the ring of regular functions. And then since we have stuff in A of Y at MP, we just have kind of this one-to-one correspondence chain. And so we can send stuff by a natural map from A of Y subscript MP into OP in an injective manner, and surjective because these are regular functions that we're working with. And so as a ring, since it's a bijective continuous map, then yes, in this case, it's an isomorphism. However, towards the dimension piece of it, the residue field of A of Y quotient the maximal ideal at P is K. And so because of that, we get that if two things have the same residue field, if nothing else, they have the same dimension. And so when Hartshorne said that line, I literally just wrote down magic. in my book because that just kind of seems too good to be true. But it is. Now for D, um, it follows from C that the field of fractions of A of y is isomorphic to the field of fractions of the ring of regular functions localized to P for every point. And then this has to be equal to K of y because every rational function is actually in some um, localization at P of the ring of regular functions. Um, Now, Hartshorne pulls out that A of y is a finitely generated K algebra, and so K of y is a finitely generated field extension of K. I don't get how those things tie together, but part of that is because it's 8 a.m. I'm willing to let that slide. um, as far as, and he says that says everything it needs to. Um, and then the transcendence degree being equal to the dimension of y is just saying that it's all of the things that we add on from K. Like y extent K is implicitly a dimensional issue of going from K to Kn. So it makes sense that that would carry over. Um, so yeah. Um, is that feeling clear enough?
Yes.
Okay. I'm gonna use the restroom real quick, and if you want to take a 5-minute break, you're welcome to, or if you want to take this time to think more about this theorem, go for it. So. Okay. So, I will admit that the next 2 pages I really struggled with um, when I went through this. And a lot of it was notation. The notation really, with the localization stuff, was badly defined in Hartshorne. It's really, unless you have a professor teaching it to you, Hartshorne's not a great introductory book. Which, I mean, like, no shit, because it's a Springer GTM. But, um, I don't know. It's a very unfriendly book, I think. Nonetheless, starting off with proposition 3.3, if we let UI open in Pn be the subset defined by xi is non-zero, where we are working with the phi I map again, by the way. So if you recall from a few lectures ago, that we were talking about that. Might have been last lecture. Basically, phi I from UI to AN is not only a homeomorphism, but it actually is an isomorphism of varieties. So before we had said we got bicontinuous biconditional map on the topology, which is an isomorphism of topologies, or really what we'll call homeomorphism. Here we're saying it also turns out to be an isomorphism of varieties. And this actually just kind of falls out of like all of the stuff that we've brought up recently. Like we don't actually need to prove this. It's just kind of obvious. Like we know that projective space is covered by affine subsets. We know that we have a homeomorphism between those subsets. If we define the ring of regular functions on each of those subsets, like as a localization, and we take the union of all of those things, we get the function field, or something isomorphic to the function field. And then if you trace that back to its residue field, you get an isomorphism of varieties. Okay. So I don't. Is that really needed? I'm looking at the next theorem and I'm like, do we need this? Yeah, we probably need it. I don't know. I mean, so theorem, hold on. This is a homogeneous prime ideal subring. Okay, hold on. No, this is important. Okay. Convention. So let S be a graded ring, meaning it can be decomposed into Z modules, and then P a homogeneous prime ideal in S, then S sub P is the subring of elements of degree 0 in the localization of S with respect to T, which is the set of homogeneous elements of S that are not in P. And then a remark is that T inverse S as a multiplicative subset has a natural grading where the degree of F divided by G as polynomials is equal to the degree of F minus the degree of G. And clearly F is in S and G is in T. Then S sub P is a local ring with maximal ideal. Some prime ideal, prime homogeneous ideal times T inverse S is multiplicative subsets intersect S of P. In particular, if S is a domain, then for P is the zero ideal, we obtain a field S localized at the zero field. So, okay, what are we saying here? We can obtain a field by localizing a homogeneous variety, a projected variety at zero. This is used for theorem 3.4, which states, y in projective space is a projective variety with S of y, its homogeneous coordinate ring. Then the ring of regular functions on y is K. And then for any point P in the projective variety, let MP contained in the homogeneous coordinate ring be the ideal generated by the set of homogeneous elements F in S of y such that F of P is equal to 0. So this is like the ideal of the variety. Then the ring of regular functions localized at P is equal to the affine coordinate ring localized at the maximal ideal generated by the variety. C, the function field, the homogeneous function field of y is isomorphic to S of y localized at 0 field. I've never used this theorem anywhere else, but I don't do a lot of projective stuff. So I don't know. I don't think I know how to prove that. Like even following the proof in Hartshorne, it's not a very like robust proof for understanding it the first time. And so yeah, I just kind of want to move on. So proposition, so essentially, if x and y are affine varieties, x is isomorphic to y as an affine variety if and only if ax is isomorphic to a of y as k algebras. And this is accomplished by alpha from the morphisms x to y being isomorphic to the homomorphisms a of y to the ring of regular functions on x, where this left homomorphism, or where this left hom is variety morphism, and this right hom is k-alg morphism. K-algebra morphisms look traditionally like vector space morphisms, just in case you haven't seen it before. And so, hold on. Let me just read through the proofs real quick, see if it's particularly important. A of y is isomorphic to a of y. That defines alpha. Suppose that y is a closed subset of an, so that a of y, the image of xi and ay. I'm going to find the inclusion map. The y be an affine variety, a map of sets, morphism if and only if. Yeah, where xi are the coordinate functions on A. Yeah, all of this just kind of makes sense. I'm looking at the proof here. It just kind of works. If you're familiar with the definitions, you can push it through. But really, the thing that this builds up to is the big theorem here is actually a corollary. And it says that the functor x sent to a of x induces an arrow reversing equivalence of categories between the category of affine varieties over K and the category of finitely generated integral domains over K. So this means that we actually have categorical equivalence. It's like an isomorphism of categories is an error reversion equivalence. And so basically we can look at affine varieties over a field K as finitely generated integral domains by basically inclusion reversing properties. And we've seen this before, we just haven't seen it categorically, right? But like our reverse inclusion lemma is where this is cropped up in the past. And so then the theorem finiteness of integral closure says let A be an integral domain, which is finitely generated, or which is a finitely generated K algebra. Let capital K be the field of fractions of A, and let capital L be a finite algebraic extension of K. Then the integral closure A prime of A in L is a finitely generated A module and K algebra. And so basically the whole point here is that the integral closure of a field extension of a field of fractions is a finitely generated A module. And this lets us look at things in terms of like vector spaces, basically. This is kind of equivalent, not equivalent, but this is related to the idea of like Hilbert's basis theorem inducing the whole finitely generated ideals thing. So the whole thing with morphisms is just like really get the definitions, really know the definitions. A lot of this is just, if I ask a problem, can you write down the definitions and can you string the definitions together? There's some computational problems in here in like the problems. But even the computational problems, like if you just write down the definitions and chug it out, it works. I'm gonna hold off on starting rational maps because I feel like we've had a lot of definitions today. Arseni, do you have any questions for the camera before we end?
No.
Okay. Then Yeah, I yeah, I wish you best of luck, and I'll see you tomorrow at 8 in the morning.
Yeah, you as well. Yeah, hopefully I'll be there. I'll be sure to verify my alarms. So, okay,
Yeah.
well, I'll see you. Thank you.
See ya. Have a good one.
You too.